and the production of concrete, the largest cost associated with the production of concrete structures and components relates to the formwork. So it's not only about reducing the material use of concrete itself during production, but also thinking about how can we bypass entirely or mostly formwork, or if we do use formwork, how can formwork be circular. So we had 3 declared aims. It's very weird that the font changed in terms of the numbering. So the first one was a circular approach towards formwork, where we were focusing on the robotic shaping of sand. The second aim, developing computational design strategies and 3D concrete printing of lattice-based screen components for both interior and exterior use, and an investigation into the ornamental qualities of concrete via additive manufacturing. Since we were focusing on sand in terms of the formwork here, you can find a lot of historic references and precedents in terms of that. So here is a selected one of sand formwork that was used for precast concrete panels for the Philips Pavilion that was developed by Le Corbusier and Yannis Xenakis for the World Expo in Brussels. Simultaneously, as shown on the render beforehand, we were really interested in this quality of the concrete, using concrete as a screen, which you normally wouldn't do, right? So concrete would rather think of it in terms of its structural purposes or structurally use to transform the space where it's in. Here, due to the fabrication process, these type of depicted components of the screen, right, they're planar. So what we tried to do is to develop double curved facade lenses out of concrete. And the very early start, we focused on the robotic sand shaping itself, testing and developing a series of end effectors for the shaping of the sand and trying to understand its behavior. We were working at room temperature and room humidity, and what we very quickly realized is that we could really be in control of the sand shaping also without adding any further additives to the sand or adding any further water. We did try experiments with spraying water on the sand, but no significant quality in terms of the surface resolution was detected. Then trying also to shape, as you saw beforehand, double curved surfaces, and then developing a strategy and an end effector where we were using this 6 horizontal oval planes to shape the sand. Overall, the sand shaping was quite fast, so to achieve the type of resolution that we needed for the sand, that was done in cycles of in 5 cycles of shaping of shaping the sand. And here you can see also our robotic setup. So we opted for dynamic movement of the robot on the tracks in order to avoid singularity and an over-rotation of the joints. The second step then was focusing on the differential growth algorithm that was selected purely for the fact that we wouldn't have any points of intersection and we could do very easily continuous printing path. We printed the first layer was always printed at the same speed with a differentiation strategy, which I'm going to talk about for the subsequent layers. And we printed up to 5 layers of the concrete. Here you can see one more time the concrete, the robotic setup and the printing. Initial testing was done first with printing, orientating the nozzle at 90 degrees towards the ground plane. There we could detect that due to this orientation, the layers of concrete, particularly the first layer of concrete was slightly sliding off the sand, which then was problematic in terms of the position of the subsequent second, third, fourth, and fifth layer, opting then for printing perpendicularly to the sand surface itself. We were following a material depositing strategy where we would differentiate between the different layer width while printing, and this was really done via the printing speed. So we developed Vertigo also due to prior testing and collaboration with Sumum Engineering. They developed an algorithm where you could really coordinate this and control it during the printing process. Then trying out also different types of openings and printing also, whereas first tests were done without printing a frame, then subsequent tests also with building a frame for future anchoring within a larger constructive system. Generally, depending of course on the number of printed layers, one of the components has a weight between roughly 17 to 22, 23 kilograms, and you can see also the shadow effect that we reached on the ground. In terms of the future steps, we're looking now into optimal reinforcement strategies for the filigrees themselves. A more further differentiated material depositing strategy according to a structural analysis, and defining or refining the interface with building components and the development of connection details to this building components. Right, very quickly now an overview of further research that we're undertaking. We moved in the last 2 years into 3D clay printing. We are using the WAS printer there that you can see, doing all sorts of different experiments with different type of pigments, trying different types of freeforms, and focusing right now on facade systems. You can see also some fails. I think due to time constraints, I'm just going to go a teeny tiny bit faster through it. Here where we use the Turing pattern to develop a facade system, a tiling system, that you can see also downstairs exhibited as part of the exhibition. Testing also different types of glazing, understanding how deformation and warping are correlated to the different burning, to the different firing temperatures, and how these can be minimized. And here also the second facade system that is also exhibited downstairs, looking into folding behavior of textiles and how this can be translated into clay, and different type of knitting patterns also translated into clay. And currently we're working on this installation that is both a wall system and also a floating structure. That is it.